All right, let's get started. Okay, a couple announcements. You should have seen your PS1 grade certainly by now. We were a little bit late getting it graded. Our goal is to have things graded by Wednesdays, so hopefully we'll do better with PS2. You may have seen your PS2 grade as well. About a third of them have been graded. The way we do it is we divide the class into, I think there are 11 TAs grading, so we divide it into groups of 11, but it's not the same TA every week. It rotates so that, if some TAs are stricter than others, it sort of averages out. But your grade will show who graded your assignment. So if you have a question about the grade, don't tell me, tell the person who graded it. And if you feel like that your grader isn't listening to you or doesn't give you satisfaction, and the lab attendance, is recorded. That's part of your grade, just being there, participating. And again, if you were there and your attendance was not recorded, should be recorded the same day, you talk to one of the TAs that runs your section. That is the same every week. So PS3 is out, and we're sort of on a roll now. We've been through 2 cycles now and starting the 3rd. Any questions or problems we can address before I start new stuff? Questions about the assignment, the course? Pardon? Still can't hear you. When is your first test? It is the Wednesday after fall break, which would be I think the 3rd week of October. Yep.
Like study guides or all the sessions before the test?
Yeah, typically we do a review. So we'll do a review the Monday before in here. I will post an old midterm for you to look at. And in the lab section, the week of the midterm, the TAs go over the old midterm. And then we usually, that's what we do. Yeah. Any other questions? Okay. I want to go back to what we were talking about last time briefly. Okay, so we were talking about accumulation loops at the end last time. And I just want to remind you what an accumulation loop is. It's a loop. So typically when you got a loop, you've got some collection of elements or values. Like a string is a bunch of characters. It might be a range of integers. It might be the tokens that are in a stream, in a scanner. So there's exactly the way that you do an accumulation depends on how the elements are presented to you. But what they all have in common is an accumulation loop combines all those elements into a single value. It may add them all up or append them all together or multiply them together, that sort of thing. So this is a prototypical accumulation loop for an integer range. So you see up here, the parameters are a starting point, which is an integer, and then the number of integers after that to consider. So if you might say, okay, start with 3 and the sequence is 4 long. So 3, 4, 5, 6. And the typical accumulation loop, first thing you do is you create a variable. I've called it ACC for accumulate here. And you initialize it to something. Typically, you initialize it to some sort of identity value. Depends on the operation you're doing. So if you're adding a bunch of numbers together, this would be 0. If you're multiplying a bunch of numbers together, this would be 1. What's this right here? What's this thing in angle brackets? Yeah? Okay, it's the type of thing you're returning. So, it may be running an accumulation over integers, but maybe we convert them to floats and add them together, or convert them to doubles and add them together, in which case this would be double. Or maybe we take them and append them all together into a string, in which case this would be string. So whatever type of thing you're trying to produce, that's got to be the type of the accumulation variable. So these two have to be the same type. Okay? Then we got to start, we start I. I is our index variable. It's going to iterate through the elements. And so we start I out at start. And then each time through the loop, we're going to get a new value of I. The first time through the loop, I will be start. The next time, start plus 1. The next time, start plus 2, and so on, until we have looked at n integers. And each time through the loop, we do something, operation, to combine the current I with the current value of ACC. So it might be just ACC gets ACC plus I, for example, if we're trying to add them all up. Then we increment I, important not to forget that. And then we return. And when we're done with the loop, we return the value of the accumulator. Right? So if you know something is accumulation loop, if you can recognize it as accumulation loop, you can exploit this pattern. But to exploit the pattern, it's not like some automatic thing. And to understand it, you know, if you, what I think a lot of students do is they just look at this like they'd be reading a story or something. What's important is to be able to figure out, be able to understand in your head what happens as time passes. That first assignment is executed, then the second assignment, then the comparison, then the two statements in the loop, then the comparison, then the two statements in the loop, and so on, till the comparison fails, and then the return. You've got to be able to play these things out in your head. If you're trying to just look at it like a static piece of text and understand it, probably not going to work at dynamic understanding of how the program evolves over time. Okay? Now, what's different? What would the prototypical accumulation loop look like if you're doing something to all the characters in a string as opposed to all the integers in some interval? What would be the same and what would change? Yeah.
Strings would have to change the type of the thing would have to return.
Okay. So he said you'd have to change the type of the thing you have to return. That's true. What else is different? Yeah.
The identity value becomes perhaps an empty string.
Again, the identity value is going to depend on what operation you're doing, and so that might be different. What else? Yeah?
So if you're looking at the characters in a string, change the while loop is just like the index value.
Okay. So here's what it looks like for a string. He said you got to cycle through the index values of the string. So you see, we just take a string as a parameter now. We set up an accumulation variable, just like before. We have I before, but now I is just counting through indexes into the character. So index 0, index 1, index 2, and so on. And then our loop runs while I is less than the length of the string. In other words, it runs as long as I is a valid index into the string. And then each time through the loop, we combine the accumulator value with the character that's at index I. So that is a prototypical accumulation loop for strings. And this is a prototypical accumulation loop for a scanner. It takes a scanner in, creates an accumulation variable, and returns it when the loop is over. And while there's another token, you combine that token and ACC into a new value. So when you're working on accumulation loops, it's, first step is to recognize it's an accumulation loop. Second step, what type of thing am I iterating over? Take a prototype, paste it in, and modify it to your needs. But you won't be able to do that unless you understand how the prototype works. Yeah?
How does it take a scanner and how would you call this in the main method?
Okay, he's asking how would you call this? From the main method, you would create a scanner, and then you would say, you would call accumulate and pass the scanner as a parameter. By the way, you can call methods from other places than the main method. Methods can call other methods. You don't have to be a main method to call another method. Okay? Now, I can't tell if you find this overwhelming or if you find this completely impenetrable and frustrating. But I do know that some of you are in each camp, and if you don't take the effort to understand it now, you're not going to enjoy the assignment, which is all accumulation loops. So, It may be necessary for you to screw up the courage to ask me a question. But about 50 other people will thank you if you do that. Yeah?
So you mentioned that methods don't need to be called necessarily in main.
Right.
If you call a method somewhere else other than main, and that method itself isn't called, will the method in question?
Okay, so he's asking if you have method 1 calls method 2, but method 1 is never called, what happens to that method 2 call? It's not made, yeah. Right. The statements in a method don't matter until the method is called.
It has to be called. Everything has to initially be called from main or from another.
Right. The types of programs we're looking at start with the main method, and if a method is not callable directly or indirectly from main, it's not needed. Yeah.
This is more of a general question. Will we ever be docked points for using information we haven't yet learned in the class or lectures or the guidebook?
Okay, so he's saying, for example, if I ask you to solve a problem and he uses a for loop, which we haven't talked about yet, would you be docked points? And the answer is no, unless I specifically say don't use a for loop. Yeah. Say again. Okay, he's asking what would you use an accumulation loop for if you're using a scanner? Who has an idea? What problem? Yeah. Okay, so the scanner is reading from the keyboard and you want to accumulate every line that the user types or every word the user types and combine it into a string and return it. Yeah. You
could use it to do
calculate what? Okay. Maybe your scanner is reading from a string that contains a bunch of number tokens and you want to average them all. Yeah?
What would be the identity value for a scanner?
Well, what would be the identity value for a scanner? We're not returning a scanner, so it doesn't really matter. If you're taking a scanner and reading integers out and adding them together, the return type would be int. If you're reading out a bunch of string tokens and appending them together, the return type would be string. Yeah?
If you're calling a method inside another method, does that have to be defined before it?
Okay, he's asking if you call a method from another method, does the one you're calling have to be defined before the other one? No. Doesn't have to. You can put them in either order. They may not even be in the same class. So you can certainly, yes, a method can call itself. That's called recursion. Yeah.
So if the type, for example, would something like that, like, what would your, how do you know what your identity value is?
Okay, so she said if the type is int, how do you know what the identity value is? The way to answer that question is, suppose, what would you do if there were no elements? What would be the logical return value? So if you were asked to add up all the numbers in a scanner, and there weren't any numbers in the scanner, what's a sensible thing to return? What would you expect? I say add up all the numbers, and here they are, and there are no numbers. What should you tell me? 0. If I ask you to multiply by convention, basically, if you're adding, the identity value is 0. If you're multiplying, it's 1. If you're appending strings, it's the empty string. Now, this is all very abstract here. So let's look at some actual code. So these are ones we did last time. So let's start right there. This is the one that multiplied in integers beginning with start. So we declared an accumulation variable. I called it product because we're multiplying things together, and I gave it an initial value of 1. So you see right away, if that loop never executes, it'll return 1. Now, How could it be that the loop will never execute? What would make the loop never execute? The body of the loop never execute? Yeah. If n is negative, we wouldn't want it to ever be negative. But if it's zeroed, it doesn't work either, right? It doesn't add anything up. Because if n is 0, then right at the beginning, I, which is initialized to start, will not be less than start. And so if you pass in n of 0, it's going to return 1, because there's nothing to multiply together. And that's fine. Okay, otherwise, what's the only other difference between this and the prototypical? I mean, what have I put here that wasn't in the prototypical loop? What specifically have I put? What distinguishes this? Well, the variable names are different. Yep. Right. This specific one right here. Product equals product times I. Is that code visible in the back? Little small? Forgot to make it bigger, so. I shall do so. Okay, so that multiplies together those numbers. That highlighted code right there is really the key. In the prototypical loop, it just said do something to combine. That's the actual combining operation. So we decided, besides picking names and types, we had to decide on that, and we had to decide on this. Otherwise, it's the same. It's exactly the same. So let's go down here and look at append ints right there. So the Javadoc says returns a string containing the n integers beginning with start, all appended together. So let's just say this is on your assignment. And I've told you, implementation note, use an accumulation loop. What should be your first step? Where would you start? People always say, I don't know where to start. So tell me where to start. Yeah. Yeah, first he said visualize what the problem's asking. You got to understand what it means. So let's do that. Suppose start is 1 and n is 3. What should the method return? Okay, it returns the string 1, 2, 3. The string that contains the digits 1, 2, 3. What if start is 10 and n is 4? What would the string contain? Nope, if start is 10 and n is 4, we'd get 1, 0, 1, 1, 1, 2, 1, 3. The numbers 10, 11, 12, and 13 glued together. Okay, so let's say we understand what it's supposed to do. What do we do now? What's our first step in coding? Yeah. Initialize what variable? He said, don't I need to initialize my variables? Which variable? Okay, do I need to initialize start and end? No, that's an important concept to understand. Whoever calls append ints will provide values for start and end. The point is, we can call append ints from many places and pass in different values for start and end. So those are parameters. So we just assume they have values. And if we're testing it, we got to provide values. If we are using it in a program, we got to provide values. Yeah. He said initialize a string that will return. There's something else I'd rather have you do first. Yeah? He said initialize I, but I don't see an I. Well, yeah. Okay. All right, so he's talking about initializing the index. No one said, well, declare. Yeah?
It's the first step by making an accumulation.
Well, no, that's not the first. Well, I'm just trying to get you to guess what I have in mind. What I called it last time was looking for inspiration. Where have you seen a loop like this before? What's the closest thing to this sort of loop that's easy to get at right now? An accumulation loop over an integer interval. Have you seen one today? We saw one 5 minutes ago. Where was it? Yeah. The product method. Right. So you think, oh yeah, Joe did this in lecture, or an accumulation loop over integers, or I did one earlier. That's a good thing to start with. Just start with the body of an accumulation loop. Now, it's not going to be exactly what you want, but until you get good at this, it's a good thing to start with. Now, let's see what's wrong with it. It says return product, and that's underlined in red. Let's see why. We're supposed to be returning a string, and there we're giving it an int. So let's take a holistic look at it. That's the prototypical accumulation loop. What type should be there? Okay, how do we know that should be a string? Because it says so right here. We're returning a string. So I will say string. Now, we probably don't want to call this thing product. What's a good name for the accumulation variable besides product? Now, ACC is very generic, yeah? Sum, well, sort of. We're going to be adding strings together, if you will, yeah? Say again. Append, yeah, appended ints. All right. Okay, and when we're all done, how do we know what we're returning down here? Yeah, typically, there are always variations on the theme, but generally you return the accumulation variable in an accumulation loop. All right, so we're appending a bunch of integers together into a string. What's the sensible value here for the initial value? The identity value, right? An empty string. You start with an empty string and you add stuff to it. And now all that has to change, because the parameters are the same, start and end, as they were in the method I copied, we don't have to go change. If this variable were beginning and this variable were j or something, we'd have to change those names. But we're lucky there. All we have to do is change this, the accumulation statement, the thing that actually does the work in the loop. So what does appended ints equal? Yeah?
Equal appended ints plus I plus the space.
Well, it didn't say anything about space, so we'll do it that way. How different is this loop from the one that came before? I mean, honestly, to me, to my mind, to my eye, they're essentially identical in all the important ways. Even, they're using a different operator to do combinations and it's different types, but it's exactly the same pattern. And once you see this pattern a dozen times or so, it starts to become very familiar to you. And you start to notice other patterns that I haven't given a name to. Yeah?
So in our assignment, it's going to be pulling out from the test method and plugging things in for I, right?
Well, the test methods will, the unit tests call your method with different parameter values to make sure it works right.
So they plug those in for I, right?
Yeah, no, they plug, when your append ints is called, the test cases will provide values for start and end. Okay? Well, let's see if we've succeeded here. I don't know, so I have unit tests, but I'm not sure if... that's product, reverse, total length. Oh, there we go, append int. So let's see what this test case does. It asks you to append the 5 integers from 1 on up and make sure that it gets back 1, 2, 3, 4, 5. And down here we call append indents with 1 and 0 and make sure we get back an empty string. So let's run it. I'm running the wrong test. And let's see, append indents says it failed. My goodness. Expected to get 1, 2, 3, 4, 5, but got 1, 2, 3, 4, 5, 6. Bad test. Yeah, the 6 numbers starting at 1 are 1, 2, 3, 4, 5, 6. Yeah, sometimes the test is wrong. So let's try this again. We'll just test append indents. And that time it passed. Okay. Doesn't mean it's right, it just means it passed those 2 tests. Okay, great. Let's look at another example. Got this one here. Returns a string containing just the lowercase letters of S. Now this is going to be a slight variation on the theme. What's different about this than any other accumulation problem we've looked at? Yep.
You're not accumulating every element?
Right, we're not accumulating every element. We're skipping some of them. We're only paying attention to lowercase letters. So it's going to be different. There's going to be something different about it. Where should we go for inspiration for such a loop? Well, let's go find an accumulation loop on strings. There was an accumulation loop on strings. Okay. So let's copy that. And notice the parameter is called S here. So if that doesn't match up, we'll have to change that. But I call that parameter S as well. Okay, now I want you to take a crack at this. Now, one thing you might notice is there are absolutely no compiler errors. Does that mean it's right? Not at all. It just means there are no compiler errors because all the names are consistent, all the types are consistent for what I copy. That isn't always the case. Talk to the people around you, take a few minutes, and see if you can figure out. Well, let's just agree. What are we going to call this? I'm going to call this lowercase letters. Okay, talk to the people around you and figure out what do we have to change to make this work, to actually return a string that just contains lowercase letters. So if the string that's coming in is capital A, capital B, little b, actually let's just look at the unit test. Now, I don't have a unit test for that, so never mind. So whatever string comes in, I want to just get the lowercase letters. Yep. That's slightly different. No, it is. Yeah, but it's wrong. It's a bad day here. Okay, let's see what you think. So is my accumulation variable the right type of thing? Yeah, that's what we're supposed to return. And does it make sense to start it out with the empty string? Yeah, typically if you're accumulating a string, it'll be the empty string. We're returning the accumulation variable there, it's fine. What about this stuff right here? And this stuff right here? That's going to be any time you're going through a string looking at characters, you're going to see that. So really, the place you need to look at is how the accumulation variable is declared and initialized, and what happens in here. Now this would just append every character to lowercase letters. We want to append just lowercase letters. So what's the obvious thing we need to do? Yes? Right. We need an if here. So if the character is lowercase, what do? Someone else tell me, what should we do if the character if character I is lowercase? Yeah.
You add it to the lowercase letter string.
Right. In fact, we do just what it says right there. So if the character is lowercase, we append it to the end of the string. Why is there not an else?
You don't have to do anything.
There's nothing else to do. If it's not a lowercase letter, we don't do anything with it. Now, how do we test if it's lowercase? Yeah?
Before the if, we can make a variable c and send that as
Yeah. We could do that, or we could just use s.charat. Yeah?
If, and then you can say, if I is greater than b or less than a.
No, the other way around. We could ask, is s.charat I greater than or equal to lowercase a and less than or equal to lowercase z? But there's an easier way. Let me get the person behind you. Yeah. Right. So there's already, just if you happen to know that there's a character class, and there's a method is lowercase, and we pass it in the character we care about, which is s.charat of I. That's sort of the cleanest way to do it. Okay? So look what I did. I took a loop, the most similar loop that I had going, pasted it in, and then I had to make, a change to it. And it looks, there's a conditional in there now, so it's sort of a conditional accumulation loop. So it takes a little bit of creativity. It's not like this is always going to be automatic. You got to think about what you're doing, but it helps to know how to find a good starting point. Yeah. Well, he's saying it doesn't convert them. It's not supposed to convert them.
Oh, okay. Yeah.
It just. So I found that the test case was sitting there. It was wrong. So if we pass it in this one right here, it should return just the string with the lowercase letters in it. And if we pass it in this, which contains no lowercase letters, we should get back the empty string. I'm confident it's right. So we'll see. Appendants. Yep, it came up green. So that's good. Okay, one more. One more accumulation loop. This one returns the sum of the integer tokens in scan. We assume that the scanner contains only integer tokens. Okay? So if we go look at the unit test for this, if we give it a scanner that is scanning off the empty string, we should get back 0 because there are no integers. If we give it a scanner that's reading off of that string, the sum of those integers is 5, and if we give it this, 1, 2, 3, 4, 5, I should get back 15. So the scanner takes care of breaking things up. I'll make that, they don't have to be single digits. So if I'll make these double digits just to drive that home. It should return what? 150? Yeah, just have to add a 0 to it. I thought something was wrong there. Okay, so there we are. Where do we go for inspiration? Well, I don't go to has next for inspiration. When I say go find the most similar loop that you've written or seen and paste it in, I'm serious. That's always, when you're learning, that's the way to do it. So where do I go? Where do I go copy? Do I copy this loop? That's an accumulation loop. Yeah, it's better if I have one that consumes a scanner right here. This reads through a scanner and accumulates an answer and returns it. Let's copy that. And you know, the scanner's called the same thing, so that's a benefit. Okay. So we've got, is this the right type of accumulation variable? Yeah, matches that. Should we call it length? No, we're adding up. So sum would seem to make sense. So I'll go rename this to sum. And is 0 the right initial value? Yeah, we're adding. So all we have to do is change what's going on in here. So before, we were keeping track of the total length of all the tokens, where the tokens were just arbitrary strings. This time, we're looking at actual values that are integers. So what do we have to change about this? Okay, does this work?
It would, assuming everything contained within the scanner was...
Well, we're assuming everything is an integer. Problem is, what type of thing is returned by next? A string. We don't want a string. We want it to convert the token to an integer. So, how can we get an integer out? Yeah. Right. Next int reads the token out as an integer. And then we might as well say, while it has a next int as well here. So the difference here is that we're dealing, before that loop dealt with tokens, looked at, just pulled, the tokens were strings, characters separated by white space. Now they're numbers separated by white space. So we need to do that. And that's the change we have to make. Yeah?
Say for example, we still had that just has next, and the last token wasn't an integer. Would that be an infinite loop?
No, what happens is, if the next token is not an integer, this returns false, and the loop ends.
I don't know, what if that was just has next? If the while condition was
No.
just has next. But the final one was
Okay. Yeah. So if you did that and the next token was not an int and it came here, there would be an exception. From your point of view, the program would crash. There are ways to deal with that so it doesn't crash. That would just be an error right now. You got to be sure when you call next int, you got to be sure the next token really is an integer token. That's why I do that. Okay? So, when you're working on these accumulation loops on the assignment, I do not want to hear from the TAs that you called them over with just the stub that I gave you, have not worked on the stub, and say, I don't know where to start. You know where to start. I've done all these examples in class. Several examples each of of accumulation loops that consume integer intervals, that consume strings, that consume scanners. You can grab these examples and pull them down using the plugin. Trivial. That gives you plenty of starting points. Okay? I'm going to assume that anyone that asked that question just either wasn't here or wasn't paying attention. It's so simple. At least do that. Then you can start doing the creative thinking. All right? Let's take a break. Then we'll look at a different kind of loop. In which window? All right, as I mentioned last time, we were doing an experiment live streaming these to YouTube. And the first experiment was not a success. The video went up okay, but the sound, I don't know if any of you have listened to it. If you listen to it for more than a minute, you're superhuman. It's just this horrible whine. I think it was basically the recording of my fan or something. I think we got the audio figured out this time. So let's hope for the best. Right, now we're going to talk about searching loops. Another common pattern. Searching loops you use searching loops when you're trying to solve this kind of problem. You've got a collection, and you want to find some element in the collection that has a property. You're not looking for the element that's the best. That's a different kind that's good enough. So like maybe you have a string, and you're trying to find in that string, you're just looking for a capital letter. You're supposed to return a capital letter that occurs in the string. You don't care which one, you just want a capital letter. That's a searching loop. You look through the loop till you find the thing you want, and then you're done. Or maybe you're going through a bunch of integers looking for a prime number. Or maybe you're going through a scanner that contains words looking for one that's misspelled. So what they all have in common is you're searching through the collection, looking at each element till you find the one that you want, or you find one that you want. There may be others that would work as well. And as soon as you find the one you want, you don't need to keep looking. You can just stop right there. That's a searching loop. So let's look at what a searching loop looks like. There's a prototypical one for integers. So what's the first thing you notice about the difference between this and a accumulation loop? Yeah? Well, yeah, that's another thing you'd notice. So there's an if statement in the body. Yeah? Yeah, you got to have the if statement. The if that's in the while loop is being used to see if the property's been satisfied. Yeah?
In the search loop, we're only returning a single value of I instead of a collection.
Well, yeah, before I wouldn't say the accumulation loops returned a collection. They've returned a accumulation of a bunch of individual elements, a combination. But you're right. We're returning an individual integer here. Yeah?
I'd say mostly it's that you have two different return statements instead of one.
Well, there are two return statements. That is true. Yeah?
We don't need to declare an accumulator variable.
Right. That's what one I had in mind. There's no accumulation variable. We start right into the loop. So this stuff here, int I is start, while I is less than start plus n, and then I gets I plus 1 at the bottom of the loop. Those are all, that's all carried over from the base numeration loop. What makes this a searching loop is just right here. So you just write the same boilerplate loop that we did for enumeration, and then you put a conditional in the middle. And the conditional says, if the current value of I satisfies the property, whatever that is, you return it right there. End of loop. So a return statement in a loop ends the loop, ends the method, and so as soon as you find what you're looking for, you're done. You return it. But what if you never find what you're looking for? Yeah? Okay, we got to return. The loop will end eventually. If we don't find what we're looking for, we'll eventually run out of elements. The loop will end. At that point, we've got to return something that indicates failure. And that just depends on the design of the method. The method will have to say, if we don't find an element, return -1, let's say. That's just an agreement with the user. So there's some value we'll use to indicate failure. So that's what you do, is you just stick that if in the middle, and you have that return that indicates failure. So let's see this in action. It usually makes a lot more sense if you actually see some code. So we're going to look at searching loops here. So here's our first one. It has, we're given an n. We're not given a starting point this time. We're starting at 1 all the time. So it returns an integer between 1 and n that has a cosine greater than 0.99. We don't care which one, we're just looking for some integer that has that big cosine. So that's a searching problem. And unfortunately, I don't have a searching loop written out. Where should we go for inspiration? I don't know. Let's go here. I will take this accumulation loop, and then I'm going to morph it into a searching loop. Got to write you a searching loop. So there we go. Okay, so we do not need an accumulation variable, because this is a searching loop. And so we're not going to do that. And we're not going to return product. What are we going to do if we don't find what we're looking for? Well, it says up there, return 0 if there's no such integer. Great. Now, why is start a problem here? Go ahead.
It's not clear.
Right. Before we were passing in a starting point, but this time what are we doing? Yeah?
We already have a fixed start at 1.
Yeah, it says always start at 1. So we'll just use 1 instead of start. Okay. Otherwise, okay, so that gets us just the bare bones. There's only one thing we have to add now. What do we have to add? The if statement. So if we have found what we're looking for, so if I is the thing if we have found the thing we're looking for, I meant to type ... but I didn't really succeed there. If we found what we're looking for, what do we return? If I is the thing we were looking for, we better return I. And now we just have to figure out if it's the thing we were looking for. Well, that's if I said if the cosine of I is greater than 0.99. And there we have it, our first searching loop. Now, if you go look in the Xi book, you won't find any discussion of enumeration loops or accumulation loops or searching loops or optimization loops, which we looked at last time. You'll just see discussions of while loops, for loops. But what I found after years of teaching this stuff is it's not enough to say to students, this is what a while loop looks like. This is how it operates. Now you can do anything. I found that it really helps to point out to students that there are patterns that occur over and over again. Probably 90% of the loops that you write will fall into one of these patterns. And nowadays when I'm programming, it's extremely rare that I've got to write a loop and I've got to stop and think. But it does happen. Sometimes there's a loop that just has a twist that I've not encountered before or not in a long time. So don't think of this as sort of I'm complicating programming by introducing these names. I'm simplifying programming by telling you there are these common patterns. Once you have a name for the pattern and you're able to recognize which pattern applies, you've got a good start on how to write the program. So what questions could it answer about this this searching loop right here? Yeah?
If you wanted to put a loop like this, searching loop, into the main method, then you wouldn't use return statements. So how would you get a value out of it?
Okay, so he's saying, what if I just... Another way to put it is, suppose that I had a method, and first I wanted to find this value, and then I want to continue on and do something with it. What would happen to these return statements? Okay, yeah? Yeah, so what we could do is, instead of returning I, you could have a variable called answer and say answer gets I. But the problem is, you do answer gets I. No, you'd have to modify the pattern a bit. So let me do it this way. So I'm going to call this, I'm going to make this be a void method. and I'm going to say print int with large cosine. And then instead of returning at the bottom, what I want to do is this. Whatever the answer is, I want to print it out. So how would I modify this thing so it doesn't return I, it actually computes a value for answer that it can print out?
Well, you have to declare.
Okay, so up here I need to say int answer. Okay. Now, when I find what I'm looking for, what do? All right, I could just store the answer there. And what do I do here? The loop ends before I want to return 0. What should I do there? Can I do this? What's the problem with that? No matter what happens in the loop, we're going to set answer to 0. This will always print out 0. So who can see how to deal with this problem? Yeah?
Use another conditional.
Well, we don't need another conditional. I can actually solve the problem by making the program simpler. Yeah? Right. I initialize it to 0. And that way, if the loop never changes the value, we're going to print out the 0. If it does change the value, we'll print it out to the new value. So that's just a slight twist, where we want to have the loop compute something, and then we want to continue on and use the answer. In this case, I'm just printing it out because that was just simple. Now, who can see not a error here, but sort of an inefficiency here? Yeah, what do you see?
You don't need to set I equal to, oh wait, no.
Well, I think you have the right, don't give me the solution. What's the problem?
Well, the problem is that I don't think you need the answer variable. I feel like it's an overcomplication.
No, yeah, I think you need the answer variable. Yeah?
You don't break out of the loop once you actually have the answer.
Right. Once you find the answer, we keep looking. Now, that's okay. We may find a different one that works, and that's okay, but it's unnecessary. So, there's a simple statement called break. Might as well introduce it here. It can only be used, well, one place it can be used is inside a while loop. And when it's executed, it just means loop over. Continue with what's below the loop. So what this does is it stores the answer we found into answer, and then the break makes the loop stop right away and pick up right here. So break is just an easy way to end a loop. Same, return ends and returns. Break just ends the loop and then picks up below the loop. Okay. So we avoid the unnecessary searching. Yeah?
Is there a way to break out of the nested loop but still continue with, say, the other loop?
Well, so he's asking about nested loops. Yeah, if you're in a nested loop, it only breaks out of the loop it's in. It doesn't break out of both. Okay? So we could live without the break, but that just illustrates an idea. Yeah?
So this only gives us the very first integer that has a cosine marker and point that next,
Right. Right.
We wanted more. The second and third.
Well, okay, so he says it only gives us the first one that has a large cosine. What if we want all of them? Okay, what's the question you'd have to answer before, if you say you want that, what question would I have for you? What? Well, not so much how many, but how do I communicate them back to you? So how would you like me to tell you all these numbers? So you pick away. Maybe you print them all out. Maybe, let's say you want me just to append them all together in a string. Okay? What kind of loop do we have then? That's an accumulation loop. That only accumulates some of the things. We saw an example of that earlier. So now we're talking about an accumulation loop again. Any other questions about this? Yeah?
So if you were to do that, would it be an infinite loop? There's infinite values of cosine that
He asks, okay, he says, wouldn't this be an infinite loop because there are an infinite number of cosines, integers that have big cosines? Why is this not an infinite loop? Yeah?
This is only till n.
Right. It only goes until I gets too big. All right, I is eventually going to get too big and end it. Are infinite loops always bad? Do you think people ever deliberately write infinite loops? Yeah. The operating system is in an infinite loop. You know, it's just constantly running, looking for something to do. Often user interfaces are written as infinite loops. So, yeah. Yeah. So in fact, with the break, it prints out the smallest integer that has a big cosine. If we take the break out, what's it going to print out? The largest one. It'll print out the last one it finds. Because every time it finds one, that'll become the new value of answer. So when the loop ends, it'll know the last one. We don't really care which, but it is a slightly different behavior. Okay. Well, let's look at another one. So this one, if a string contains a digit, returns it, otherwise returns the underscore character to say that there wasn't one. So where should we go for inspiration for this? We're given a string. We've got to find a digit and return it if we can. Yeah?
We take kind of some hybrid between that search loop and that scanner accumulation.
Okay. Yeah, so this is, again, he said, what he basically said was, let's go get some inspiration from a string loop we wrote before to accumulate, and that searching loop we just did. Generally won't be a problem, because we'll have a searching loop for strings lying around. This is the first one we've written. So I'm going to go back to accumulation loops. Here is a string loop we wrote. I'll grab it. And we'll modify it into an accumulation loop for strings. So I will just, I'll leave that return so I won't forget about it. Okay. That's the accumulation loop. What's it going to take to turn it into a searching loop for strings? What do we get rid of? What about this? Right, that's the accumulation variable. We don't need that anymore. And we don't want to return the result of accumulating. We get rid of that. And this is what is doing the accumulation, so we get rid of that. So there's a skeleton of the loop. It goes through all the characters. When it's done, if the loop ever ends normally, if there's not a return inside, it's going to return sort of our failure answer. It says there wasn't a digit. So what's left to turn it into a searching loop? What do we put in that blank space? An if. So if we have found the character we're looking for, I don't know why it does that. I thought it was my bad typing, but it just wants to insert i's when I type ... What do we do if we have found a digit? If we find a character that's a digit, we return it. Yeah?
When the comment says return it, does it mean the string or the digit?
The digit. Yep, that's fair. You can tell because the return type is char, not string. Now, it may be you get tired of typing. So up here, you're going to have to say something like, is s.charat of I a digit? And you get tired of doing that. So one thing you can do is this. Just do that once. And then just, if C is a character that is a digit, you just return C. So you just call it C everywhere else, instead of constantly having to say s.charat I. So what's the test? How do we tell if C is a digit? Yeah, it'd be nice. Maybe there's a character dot. It's always worth looking. Is digit. We're in luck. And we're done. So all we had to do is, the specification said that's what you return on failure. We just had to figure out that. Well, really, should include the line above it. We added that for the specific application. If the character is an I, if we pull the character out, if it's a digit, we return it. If we never find a digit, we return underscore. Searching loop on strings. Now, on the next assignment, the one you're working on right now, PS3, you can solve all the problems with accumulation loops. Because PS3 covers what we did last week. Now, you may find some that you think, I'm going to use a searching loop for this. And there's one where that's possible. But in reality, you can solve them all with accumulation loops. Any questions I could answer about this? Well, this is a variant here. I'm gonna skip over the variant. These will be accumulation loops that do conditionals. Let's do this one right here. Find word of length. So it says if the scanner contains a token of the desired length, returns it, i.e. the token. Otherwise, returns the empty string to indicate failure. Right, so we got to consume the contents of a scanner until we find a token of the right length. And when we do, we return the token. So where should we go for inspiration? What do you think? What's the closest loop we've written that deals with scanners? Yeah? All right, we'll go to a scanner accumulation loop. Here we are. So I'll copy that. And we'll go here. And I'll paste it here. And I'll get rid of the accumulation variable. And I'll get rid of returning the accumulation variable. And I will get rid of the accumulation operation. And there's not much left. But there's an error. Why is there an error? It doesn't know what SCN is. It's just because I called it tokens here and SCN in the other method. So I'll just call it tokens here, and then we're good. So there we're getting started. All we have to do is put a conditional in here that checks. It looks at the next token and figures out. Well, how can we figure out, well, what do we do if we find a token that works? What do we return? Okay, I'm going to try to do it without declaring a new variable and see what you think of it. So, how do we know if the next token is the thing we want to return? How do we get the next token? Scan.next. Tokens.next. And how do we figure out its length? And how do we know the length is what we're looking for? Equals desired length. So we get the next token, and if its length is the one we wanted, we have found a winner. Now, before I go on, I want to point something out to you. This is not like a history class. Now, I'm probably doing a disservice to history classes, but I imagine a history class, if you miss the week when they talk about the Civil War, you can presumably pick up the next week when they're talking about Reconstruction, and at least pass that part of the test. But in this class, if you checked out during the week where we talked about methods, objects and methods, that's no good. It all accumulates. It's not like you're going to be sitting, making millions of dollars as a programmer in the future saying, man, I really hated that time we had to learn about methods. I'm glad I don't have to do that anymore. It's not going to work. This all builds. And so right here, I'm assuming that, okay, you did a whole assignment on methods, on objects, and that you know how to do it. So you got a scanner. This gives you the next token. That's a string. You can take the length of the string. And what mistake have I made? Well, I didn't make a mistake yet. I'm getting ahead of myself. What do we do when we find the token? We just found the token we're looking for. What should we do? Return it. Now, I know some of you understand the mistake I just made. I want the rest of you to think about it for a few seconds anyway. I just made a terrible mistake. This is going to return completely the wrong thing. And it happened when I typed tokens.next. Now, I want to hear from someone who this just occurred to, didn't see it coming. Now, everybody putting their hands down. Okay, did it just occur to you?
Maybe. So when you do the tokens.next, and then when you follow it the same again, go to the next.
Right. What he said was, we call tokens.next, that gives us the next token, and we decide we want to return it. But what does this give us? The one after that. This is an easy mistake to make. I've made it more than once. So what's the solution? Back there. Right. We will just declare a variable called token, and we will set it to be tokens.next. So we get the next token and save it somewhere. Then we can just talk about it as token. And if token is good, we return it. We don't want to call token.next twice. Why did it work? Why would it work if we called s.charAt twice? Why'd that work and this won't? Yeah?
Find a specific location that you want the character to be at. With this, you're taking the next or following set of characters.
Okay. So to paraphrase, calling s.charAt of I does not change the string in any way. And so if you call it again with the same I, you get the same answer. Calling tokens.next not only gives you a token back, it changes the scanner. So that when you call it again, you get yet another token. So you need to do that. So I said I make that error a lot. I'll show you another error I make a lot. And I made it today, actually, when I was preparing for lecture. It's forgetting this. I mean, how many times I've written a loop like this and I forget the I equals I plus 1 part. Forget to change the loop variable. If you're about to ask about I plus plus, okay. Yeah, I'm going to defer discussion to that. There are shorter ways to do this, but right now I'm happy with the way we're doing it. Great. So we got this loop now that can find a digit, a searching loop. Yeah?
So if you forgot that I equals I plus 1, is it just redoing the same loop for the same?
Right. So if you leave this out, you might get an infinite loop. There's one circumstance in which you would not end up with an infinite loop. Actually, I can think of a couple. If I never changes, how could this return something anyway? Yeah. Right. If it either loop never runs because the string is empty, or the first character happens to be a digit. Otherwise, I never changes, and we just keep asking the same questions over and over again and never returning. So yeah, it's pretty obvious what you've done wrong when you do it, but I still keep doing that. Yeah?
The one you just did with the find word length,
Mm-hmm.
can you do something similar to that on that one just to make sure it doesn't run infinitely?
Well, here, what makes this one not run forever? It's because when we call next, we're actually modifying the scanner. We're pulling something out. So eventually the scanner will empty out, in which case this will stop us. All right, let's write one more. Here's a method. It takes in a positive integer. It takes in n, which is supposed to be positive. I guess I didn't write that down. Well, I guess it doesn't matter. I want it to return, given n, return the number of factors that it has, number of positive integers that are factors. So what would be number of factors of 1? How many positive integers are factors of 1? There's only one, which is 1. What about 6? 4. 1, 2, 3, 6 are all factors of 6. So I just want to count factors. So where do we go for inspiration? Okay. What is it? A searching loop? We're not searching for something and then returning it. What do we? So it's not a searching loop. Yeah? It's more like an accumulation loop. It's like sort of a conditional accumulation loop. You got to look at everything. You got to look at a bunch of numbers, and whichever ones are. So this is like, let's see, we did a loop like that. Let's see what the closest. Where do we have an accumulation loop with an int in the middle? Okay, it was. Well, that's a string one though. That's too bad. Right, let's find one that works on ints. Let's use this for inspiration. Or maybe not. Okay, I got time. Let's do this. That's an accumulation loop. Maybe we could find a better one. But I just said this isn't really a... So let's see. What should we call our accumulation variable? Factors, sure. I'll call it n factors. So we're going to use that to count. Where should we start our counting from? It makes sense to start counting from 0. When we're all done, we're going to return our accumulation variable. So that's going to be n factors. Okay, we start at 1, right? We're only looking at positive. Well, what do we look at? If you're trying to find factors of n, what numbers do you have to consider? Yeah? Less than or equal to, because the number can be its own. So we'll start with 1, and we'll keep going until we get to n. So we look at all the numbers from 1 to n. And when we find a number that's a factor, we need to add 1 to n factors. So how do we tell if a number is a factor? How do we know if I is a factor of n? Yeah? All right, so we say if n mod I is equal to 0, if the remainder we divide by I is 0, then we need to add 1 to n factors. So it's all right. It always comes a time when I just get tired of typing that. All right. There's that sort of thing right there. Just says add 1 to the variable. It's the same as saying n factors equals n factors plus 1. Yeah. That works too. You can put the plus plus in the beginning. You see, that's why I don't do that, because I don't like having to explain this so early in the class. So I'll explain the difference after class. All right, so we've written sort of a conditional accumulation loop here. We start our thing out at 0. We return the accumulation variable when we're done. It's just that we only accumulate when we see a factor. Okay? Does it work? Well, I'm out of time. I don't know. We'll see next time. I'll leave a cliffhanger.